Hello, this week we are going to continue talking about electrophilic aromatic substitutions on aromatic rings. This time we're going to do it with a carbocation as our electrophile. The first people to do this were Friedel and Krafts. So we're going to use a modification of a Friedel-Crafts type reaction to create this molecule that looks complex. The tetraphenylporphinate, the porphyrin is this part of the ring. And this is a part of the ring that we see in other structures in biological systems. We see it in the heme. We see it in chlorophyll. And so the formation of this structure does have some biological relevance as well. But for us, it's using a carbocation as our electrophile that is going to be the new thing. So this is just showing the structures. This is the molecule porphin, the parent structure of all of these molecules. We're going to create the tetraphenyl derivative of this. But you can see, right, the elements of the porphin are nitrogen-containing rings that are aromatic and bridges between them of one carbon that are unsaturated. So that's what we're going to do. And we can see that parent structure within our heme and within our chlorophyll structure. So it's that parent structure that we're going to make in our reaction this week. So this is our product. You can see that porphin product. We're going to substitute a copper 2 ion in the center. But you can see, while it looks complex, we're going to make it out of this part is going to be made from benzaldehyde. And this part is going to be made from an aromatic nitrogen-containing compound called pyrrole. And so we're going to use those two components to create this ring using carbocations as the electrophile. So if we just want to review our electrophilic aromatic substitution quickly, we introduce an electrophile. That electrophile attracts electrons from the aromatic system to create a new bond. Right? There's our new bond. That disrupts the aromatic system and creates a carbocation. But aromatic systems are unusually stable. So if we were doing addition, a nucleophile would come in here. But the aromatic system is so stable, the molecule wants to return to that aromatic system. So a base comes in, takes the extra hydrogen ion, the electrons from the carbon-hydrogen bond fall back to create the pi bond again, and we have replaced our hydrogen in our starting molecule with the group derived from our electrophile in our ending molecule. Now, in the classic Friedel-Crafts reaction, Friedel and Kraft were generating carbocation electrophiles. Now, the problem is a carbocation electrophile is difficult to form in high enough concentration to react with the very stable aromatic system. And so they needed to increase the yield of carbocations in order to get effective reaction with the relatively stable aromatic system. And so they needed to use an inducement. That is, they used a strong Lewis acid, and they used aluminum chloride as the Lewis acid. The aluminum chloride would form a complex with the halogen on the alkyl halide. That would increase the effectiveness of the halide as a leaving group, and you would get a higher yield of your carbocations that could come up here and act as an electrophile. In some ways, it's analogous to what we've done before. That is, we can use, right, and my positive charge is not showing here, but I will replace that, right? We can use a hydronium ion, right, as an acid to protonate our oxygen to make it a better leaving group. We can see the positive charge sort of is hidden there. And then when the leaving group leaves, we can get a greater yield of our carbocation. So we have, in the past, we used this reaction as a way of generating carbocations in a Friedel-Crafts-like reaction. But you can see that the aluminum chloride with the chloride ion leaving group here, is playing a similar role to the hydrogen ion and the hydroxyl leaving group there. So we were able to generate carbocations to get carbocations acting as electrophiles. The problem with this reaction is aluminum chloride is difficult to work with. It is a strong Lewis acid, and it is somewhat dangerous to handle. And so we didn't want to do that in our laboratory. And so we needed to come up with alternate ways of creating carbocations in high enough yield that we could get an effective electrophilic aromatic substitution. So here's how we're going to generate carbocations in our reaction mixture. So this starting molecule is benzaldehyde. And this is propanoic acid. And so we will use the unshared pairs of electrons on the carbonyl of benzaldehyde as a base. It will be protonated by the propanoic acid, and when we protonate that, you end up forming a carbocation. And so then our pyrrole ring can act as a nucleophile and attack that carbocation to create, and when I copied my structure, again, my positive charge didn't show. So we'll put our positive charge on our intermediate right there. Right? So there is our carbocation aromatic intermediate. Our propanoate can act then as base to take the extra hydrogen ion. The electrons in that carbon-hydrogen bond can fall back into the aromatic system, and we have modified our pyrrole. And just to clear things up, apparently in my copy, we lost a little bit of our ring. Okay? So that is the first electrophilic aromatic substitution. Right? Our electrophilic carbocation replaced the hydrogen that was there. That hydrogen now has been replaced by this hydroxy benzyl group. Right? So we've got a hydroxy benzyl group on our pyrrole ring. So, In order to complete the bridge, we need to create a second electrophilic carbocation. Carbocation. Apparently, I got a little excited when I was typing, so we'll just mark out one of them. Right? So, our propanoic acid, again, will act as a Bronsted-Lowry acid and protonate our newly formed hydroxyl group on our substituted benzaldehyde. So we will protonate that, right? Electrons will take the hydrogen ion, leaving the propionate. That will give us water as an effective leaving group on a secondary carbon, also next to aromatic rings that would stabilize a carbocation. So this carbocation, when our water leaves, we create a carbocation that is not only secondary, it is also stabilized by resonance with this aromatic ring system, and it is stabilized by resonance with this aromatic ring system. So this is a very stable carbocation that is very easy to form. And now that we have a carbocation, we can get a second nucleophilic attack by a pyrrole ring to create a second electrophilic aromatic substitution. So our pyrrole ring attacks, right? There is a hydrogen on, there is a hydrogen right there. We get a nucleophilic attack on our new carbocation, right? That disrupts the aromatic system. Our propionate is in there. It can act as a base to deprotonate that intermediate, allowing these electrons to fall back in and restore the aromatic system. And we have bridged two pyrrole rings with a benzyl group, actually a phenylmethynyl, here it is down here, a phenylmethynyl bridge is connecting two pyrrole groups. And so now this position of this pyrrole and this position of this pyrrole are available for another round of the electrophilic aromatic substitution. So we get EAS going on here and going on here to create another starting phenylmethynyl bridge. So we create another bridge, put another pyrrole, another bridge, another pyrrole, and we work around that way. So you create another bridge, put another pyrrole, create another bridge, put another pyrrole, create another bridge. That will give us our 4 pyrroles and 4 bridges. And so after we do all of those reactions, this is our product. Now, at the moment, we will leave this product unnamed. That is its formula, C44H36N4. We're not done, right? Our pyrrole has a particular aromatic ring system that we have to recreate. Now, luckily for us, we don't have to do much. We're just going to deal with spontaneous oxidation in air, right? Just the presence of air as we work this up, right? The presence of air as we work this up oxidizes this to form our final tetraphenylporphin, right? There's our final tetraphenylporphin. Now, note in here, we've got 2 of the hydrogens, Two of the nitrogens in our tetraphenylporphin are protonated. Two of them are not. Right? In that structure. We're going to make use of that because now our challenge is, how do we put a metal, a copper, right there in the center? That's our challenge. Okay, so to put our copper in the center, we are going to do one of our favorite things, which is to reflux in order to heat this without losing material. And we use copper, right? Here's our copper 2. And we're going to use copper 2 acetate. We're going to use copper 2 acetate in part because it's a nice, with acetate, it is a nice soluble form of copper 2. So it will release copper 2 rather quickly in solution. But also, the acetate ions are themselves basic. And so we are going to use the basic acetate ions to accept the hydrogen ions from the nitrogens to create 4 potential coordination spots for our copper 2. And so when we deprotonate that, our overall ring becomes 2-, but our copper is 2+, so our overall complex has 0 charge. If we look at our overall reaction, right, in order to get whole numbers, right, in order to get whole numbers of oxygen, we have to look at creating 2 molecules of the tetraphenylporphin. So to make 2 molecules of the tetraphenylporphin takes 8 moles of the benzaldehyde, right? There's the important information about that. It's also in your handout. 8 moles of your pyrrole, again, essential information given. Oxygen from the air, so we have to assume that is in excess. Because we regenerate our propanoic acid, it is catalytic in the process, right? It protonates the benzaldehyde, but then it deprotonates the aromatic carbocation intermediate, and so it ends up being catalytic in the process, and so it takes 8 moles and 8 moles to make 2 moles. Our reaction apparatus is going to look a little different than we've used before. We want to be able to reflux, but simultaneously we want to be able to add. And so we're going to set it up using the Claisen adapter, right? This piece of glassware is called the Claisen adapter. And so the Claisen adapter lets us split our fittings. And so in the fitting directly above our round bottom flask, we will use a separatory funnel as an addition funnel. That is, we can put things in our separatory funnel and use the stopcock to add them without opening up our system. But yet we can still have an open system that is available for reflux. So your refluxing solvent will come up here and run back down and back into your flask. So it lets us set up for addition and reflux simultaneously without having to go back and forth in terms of our glassware. And so if we look at the experimental details, a couple of things you need to think about. Note, they do some things, I wrote this lab after a hint from Mr. Wyeth that it might be interesting. Note, they tell you how much propanoic acid to add, but they don't tell you how much benzaldehyde to add. They give you a number of moles, right? So benzaldehyde is a liquid. So what information do you need to effectively measure out that many moles of benzaldehyde? Okay? While your mixture is coming to a boil, again, we're going to mix propanoic acid with, again, a volume of propanoic acid with a number of moles of pyrrole. So again, what information do you need to measure effectively that number of moles given its state? If it's liquid, you want to convert it to milliliters. If it's solid, you want to convert it to grams, right? What is the most effective way of measuring that? So, we're going to do additions, again, through our separatory/addition funnel, and then we will isolate the crude product of our pyrrole in a fairly straightforward manner. Okay? So, the first part is making our tetraphenylporphin. And then we have to get a metal in it. So, to put a metal in it, right, to put the copper 2 in it, or possibly other metals, we will only use 0.2 grams of what you made. We hope you made more than that. Your theoretical yield should be more than that. So we hope you made 0.2 grams of your tetraphenylporphin product, right? We're going to use dimethylformamide as our solvent. However many grams of this, you need the same number of moles of copper 2 acetate monohydrate. So again, you've got some grams to moles calculations that you're going to have to do at the time. If you've got less than 0.2 grams, you'll have one amount, right? So however much of this you weigh will determine how much of the copper 2 acetate you use. We will reflux this gently and collect the product. And we hope that we can note changes in appearance after we add the copper 2. Right? So there are lots of good observations in this lab for us to write down. We've got a couple of different processes we're doing. We're doing a standard reflux in this part. We're doing the modified reflux as we're creating our tetraphenylporphin. If you have any questions, please let me know. This is, in place of your normal lab introduction.